Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 9, Rotation Motion. Rotation. Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 9, Rotation of Rigid Bodies, Video 1. Today's topic is angular velocity. The objectives are: know the definition of angular displacement, angular velocity, and angular acceleration. Be able to convert between degrees, radians, and revolutions. Be able to describe the rotation motion of a rigid body in terms of angular coordinate, angular velocity, and angular acceleration. Angular coordinate. Now let's consider a rigid body that rotates about a fixed axis, such as a clock for the second needle going around the clock or a minute needle going around the clock. An axis that is at rest, in this case, would be an axis pointing out of the clock. In some inertial frame of reference, such as Earth, and does not change directions relative to that frame. Another example could be a speedometer or even the spoke of your stationary bike. Those are all rotations around a fixed axis. So here is a diagram. This is a theta. Is measured from positive x-axis specify the needle's rotational position. So in this case, it's counterclockwise. An axis of rotation passed through the origin pointing out of the page. So we use the angle theta as a coordinate for rotation. Theta is the corresponding to displacement. Much like the displacement of particle moving along a straight line, the angular coordinate theta of rigid body rotates around a fixed axis can be positive or negative. The convention is counterclockwise is positive, clockwise is negative. To describe rotational motion, the most natural way to measure the angle is not in degrees, but in radians. Sometimes we also use revolutions. So let's take a look at the relationship between displacement in revolution, degrees, and radians. So one revolution is going one round. So going from this position, going one round, going back. In one revolution, there are 360 degrees. Now, the radian is the ratio of two lengths, the length of this arc and the length of radius. So it is a pure number without a dimension. So that's called a radian. Radian is just number. How many radius does this length have? That's what it means. So 1 radian is 1 of radius, right? 2 radian is 2 of radius. So it turns out in a circle, how many radius in a circle? That's about 6.28 radius in the whole circle. So in one complete revolution, there are 2 pi radians. So relating the two, 360 degrees equals to 2 pi radian, or 1 radian equals to 57.3 degrees. So relationship between the angle in radian, the length of the arc, and the radius are theta equals the length of the arc divided by r, like how many radius the length of the arc has. So the length of the arc equals r times the radian, the angle in radian. Average angular velocity is in radian per second or RPM. So angular velocity is the angle swept out divided by the time it took to sweep out the angular displacement. So at T1, your position, angular position is theta 1. At T2, your angular position is theta 2. So between the delta T, your delta theta is theta 2 minus theta 1. So average angular velocity is changing angular position divided by change of time. So we use the symbol omega to represent angular velocity. Angular velocity also can be measured in RPM. So in this equation, it's radian per second. So RPM is revolution per minute. In one revolution, there are 2 pi radian, and 1 minute has 60 seconds. So 1 RPM equals to 2 pi over 60 radian per second. We have this z subscript. Z indicate that the body is rotating about x-axis, which is perpendicular to the plane of the diagram. It's coming out of the screen in this case. Angular velocity is a vector quantity. You can visualize the position of the vector by sweeping up the angle with the fingers of your right hand. Remember right hand rule we learned before? The position of your thumb will be the direction of the angular velocity vector. This is called the right hand rule. Let's take a look at the picture. If you are going counterclockwise, your thumb will be pointing upward. And hence this up is defined as positive because counterclockwise is positive. Your thumb direction of omega is upward. Now, if the object is rotating clockwise, your thumb would be downward. So positive is up, negative is down. So again, counterclockwise for your theta is positive, so result positive omega. And clockwise, theta is negative, result negative omega. Instantaneous angular velocity and angular speed. The instantaneous angular velocity, omega z, is the limit of the average as time approaches to zero. The definition is the same as instantaneous linear velocity. So it's a derivative d theta over dt. So we simply refer the angular velocity as instantaneous velocity. Otherwise, you will be given to calculate average angular velocity. If we just say calculate angular velocity, that means it's instantaneous angular velocity. The angular speed omega is the magnitude of angular velocity. Just like ordinary or linear speed, the angular speed is never negative. So it can be rotating counterclockwise or clockwise, it's just a number. Question, angular velocity versus linear velocity. So angular velocity, omega z, is ordinary velocity or linear velocity, Vx, they are different. So if an object has velocity Vx, the object as a whole is moving around axis. By contrast, if an object has an angular velocity omega z, then it is rotating around the z-axis. It's not moving around the z-axis. See? The different points on a rotating rigid body moves different distance in a given time interval, depending on how far the point lies from the rotation axis. Think about when you going on merry-go-round. If you are going further on the edge, you're going a lot faster. Even though if you're going closer to the center, you are going very slow. I'm talking about fast and slow is about your linear speed. But every point, it doesn't matter you're going far or closer to the center, you are rotating with the same angle. So all points rotate through the same angle in the same time. Hence, at any instant, every part of rotating rigid body have the same angular velocity. However, the linear velocity is different, right? The angular velocity is positive if the body is rotating counterclockwise and negative if it's rotating clockwise. So those are two different concepts, angular velocity versus linear velocity. Now let's take a look at our first example. So a flywheel of a prototype car engine is under test. The angular position theta of the flywheel is given by this function, theta equals to 2.0 radian per second cubed times t cubed. The diameter of the flywheel is 0.36 meters. Find the theta in radian and in degrees at time t equals to 2 seconds and t equals to 5 seconds. Well, to find the theta equals to 2 seconds, we simply substitute t equals to 2 seconds here and find the theta. 2 times 2 cubed will give you 16 radian. That's in radian. How do you convert radians in degrees? 1 radian, we know 2 pi radian is 360 degrees. So in this case, radian cancels, you have degrees. The degree is 920 degrees. Now, similarly, you can do 5 seconds. 5 seconds is 250 radian, that's 14,000 degrees. Next one, find the distance the particle on the rim moves during that time. Remember distance, S equals R times theta. So during that time interval would be R times delta theta. Delta theta is 250 minus 16. In this equation, theta has to be in radian. So we use 0.18 times 250 minus 16, you'll have 42 meters. Next one, find average angular velocity in radian per second and in revolution per minute between t1 equals 2 seconds and t2 equals to 5 seconds. The average angular velocity, omega, equals to change of theta divided by change of t. Substitute your given quantity, you'll have 78 radian per second. Now we have to convert radian per second to RPM. 1 radian, 2 pi radian is 1 revolution. And we have to convert second to minutes. So 1 minute equals to 60 seconds. This way, second and second cancels, radian and radian cancels. All you have is REF, revolution, and a minute. That gives you 740 rev per minute. Lastly, find the instantaneous angular velocity at time t equals to 5 seconds. Instantaneous angular velocity is the derivative d theta over dt. So that gives you 6t squared. To find instantaneous angular velocity, we simply substitute t equals to 5. You will have 150 radian per second. Next concept is angular acceleration. Angular acceleration is the change of angular velocity divided by the time interval during which the change occurred. The symbol alpha is used to denote angular acceleration. So alpha equals to omega, change omega divided by change of t. The instantaneous acceleration is derivative d omega over dt or d double derivative theta over dt squared. Again, angular acceleration is a vector quantity. Angular acceleration vector will be either parallel or antiparallel to omega. So when it's parallel to omega, you are speeding up. When it's antiparallel to omega, you are slowing down. Let's take a look at this example. So you are given omega equals to 6t squared. That's what we derived from last example. What is the average angular acceleration between t1 equals to 2 and t2 equals to 5? To find that, we have to find omega at 2 seconds and omega at 5 seconds. Then we simply substitute into the equation, you have 42 radians per second squared. To find the instantaneous angular acceleration, we have to do derivative. Derivative equals to 12t. And to find instantaneous acceleration at t equals to 5, we substitute t equals to 5 here. You have 60 radian per second squared. Last part, test your understanding. So you're given the graph. Omega is the green line and alpha is the yellow line. So during which time interval is the rotation speeding up? We know speeding up, alpha and omega has to be in the same direction. So that's in these two regions. So the answer is 1 and 3. During which time interval is the rotation slowing down? For it slowing down, the two must be having opposite direction. So it's in this region. That's number 2. That's it for today. Thanks for watching. See you next time.